Have you ever stopped to think about the unsung hero of our modern world? It's not the internet, not the smartphone, but the humble battery. Without it, our portable, interconnected lives would grind to a halt. Today, we're going to unplug from the grid and dive into the fascinating, centuries-long story of the battery. How do we go from a mysterious twitching frog leg to the powerhouse in your pocket? Stick around, because this story is truly electrifying. Our journey begins not in a modern lab, but in 18th century Italy with a bizarre discovery. Imagine this: scientist Luigi Galvani is dissecting a frog. He touches its leg with two different metals, and suddenly, the leg twitches as if it's still alive. Galvani believed he had discovered animal electricity, a life force inherent in living tissue. It was a fascinating idea, but it was another Italian scientist, Alessandro Volta, who correctly interpreted the phenomenon. Volta realized the electricity wasn't coming from the frog, but from the chemical reaction between the two different metals in the moist environment of the frog's leg. This was the eureka moment. Volta set out to prove his theory. He experimented by stacking discs of zinc and copper, separating them with pieces of cloth soaked in salt water. When he connected a wire to the top and bottom of the stack, it produced a steady, continuous electric current. In the year 1800, he unveiled his invention, the voltaic pile. This was the world's first true battery. It was clunky, it wasn't very powerful by today's standards, but it was a revolutionary device that could generate electricity on demand. For the first time, humanity had a portable and reliable source of electric power, opening the door for a whole new era of scientific discovery. Before the battery, life was, well, stationary. The only sources of electricity were fleeting and unpredictable, like static electricity or lightning strikes. You couldn't just carry power around with you. If you wanted light after sunset, you used candles, oil lamps, or gas lights. These were fire hazards, produced soot, and offered limited illumination. Communication over long distances was painfully slow, relying on messengers on horseback or by ship. The idea of instant, global communication was pure fantasy. Life was tethered to the daylight hours and the physical limitations of fire and steam. The world was a much darker, quieter, and slower place. The battery was about to change all of that. Following Volta's breakthrough, the 19th century became a hotbed of battery innovation. In 1836, a British chemist named John Frederick Daniell created the Daniell cell. It was a big improvement over the voltaic pile because it was more stable and lasted longer. This made it perfect for powering the new wonder of the age, the telegraph. Suddenly, messages could be sent across continents in minutes, not weeks. The world felt smaller, more connected, all thanks to this improved battery. But the real game changer came in 1859 with the invention of the rechargeable battery by French physicist Gaston Planck. He created the lead-acid battery, a design so effective that a refined version of it is still used to start most cars today. Think about that: the basic principle behind starting your car was invented over 160 years ago. For the first time, a battery didn't have to be thrown away when it ran out of power. It could be restored, reused, and relied upon again and again. This concept of rechargeability was revolutionary, paving the way for true energy portability. So, how do we get from these early, clunky contraptions to the sleek, powerful batteries we use today? Let's take a behind-the-scenes tour of a modern battery factory. While the specific chemistry has evolved, the fundamental principle Volta discovered remains the same: a chemical reaction that creates an electrical current. Today's most common rechargeable battery is the lithium-ion battery. The manufacturing process is a marvel of precision engineering. It all starts with the raw materials. The key components are lithium, cobalt, nickel, and graphite. These materials are mined from the earth, often in places like Australia, Chile, and the Democratic Republic of Congo. The mining and sourcing of these materials are complex topics in themselves, with significant environmental and ethical considerations that the industry is actively working to address. Once sourced, these raw materials are processed into highly pure powders. These powders are then mixed into a thick, dark slurry, which looks a bit like paint. This slurry is the active material that will store and release energy. Now comes the coating process. Huge machines apply an incredibly thin and perfectly uniform layer of this slurry onto long sheets of metal foil, typically copper for the negative electrode or anode, and aluminum for the positive electrode or cathode. The precision here is critical. Any imperfection can affect the battery's performance and safety. After being coated, these giant sheets are dried in long ovens, then pressed under immense pressure to ensure the right density and thickness. Following this, the coated foils are precisely cut into smaller electrode sheets. Now, we need to assemble the jelly roll. A machine takes a sheet of the cathode, a special porous plastic sheet called a separator, and a sheet of the anode, and winds them together into a very tight, compact roll or stacks them in layers. The separator is crucial. It keeps the positive and negative electrodes from touching, which would cause a short circuit. This jelly roll is then inserted into a metal can, usually cylindrical or a flat pouch. A special liquid, the electrolyte, is injected into the can. The electrolyte is the medium that allows lithium ions to flow between the anode and cathode when the battery is charging and discharging. Finally, the battery is sealed, charged for the first time in a process called formation, and then rigorously tested for capacity, voltage, and safety before it's shipped out to become the heart of a new device. It's an intricate dance of chemistry, physics, and engineering, from powering early telegraphs to starting our cars. Batteries have always been at the forefront of technological advancement, but in the late 20th and early 21st centuries, their role exploded. The invention of the lithium-ion battery in the 1980s was the catalyst. These batteries were much lighter, held more energy, and could be made in various shapes and sizes compared to their predecessors. This breakthrough unlocked the era of personal portable electronics. First came the Walkman, then laptops, digital cameras, and eventually, the device that changed everything, the smartphone. Your phone is a supercomputer, a camera, a GPS, and a communication hub all in one. And none of it would be possible without a compact, powerful lithium-ion battery. We went from being tethered to wall outlets to carrying the entire world's information in our pockets. But the battery's impact doesn't stop there. They are now at the center of two of the biggest technological shifts of our time: electric vehicles and renewable energy. Electric cars, once a niche curiosity, are now going mainstream, all thanks to massive, sophisticated battery packs that can store enough energy to travel hundreds of miles on a single charge. They are helping us transition away from fossil fuels in transportation. Simultaneously, batteries are solving the biggest problem with renewable energy sources like solar and wind. Intermittency. The sun doesn't always shine, and the wind doesn't always blow. Large-scale battery storage systems, often called big batteries, can store excess energy generated on sunny or windy days and release it back into the grid when it is needed, ensuring a stable and reliable power supply around the clock. These massive battery farms are becoming a critical piece of our future energy infrastructure. The story of the battery is far from over. Researchers around the world are in a race to create the next generation of batteries. We're talking about solid-state batteries, which promise to be safer, charge faster, and hold even more energy. Imagine an electric car that could be fully charged in the time it takes to fill a tank of gas, or a smartphone that lasts for a week. Other promising technologies include sodium-ion batteries, which use abundant and cheap salt instead of rare lithium, and even structural batteries that could be built into the body of a car or an airplane, saving weight and space. The future powered by batteries is one of greater freedom, sustainability, and connection. From a simple frog leg experiment to the complex systems powering our cities and exploring space, the battery has been the silent partner in human progress. It has empowered us, untethered us, and continues to drive us toward a brighter, more sustainable future. So the next time you pick up your phone, get in your car, or even just use a TV remote, take a moment to appreciate the incredible journey of that little power pack. It's a story of curiosity, ingenuity, and the relentless human drive to innovate. What started with a twitching frog leg now powers our entire world. Thank you so much for joining me on this journey through the history and future of the battery. If you found this interesting, don't forget to hit the like button, subscribe to the channel, and ring that notification bell so you don't miss our next deep dive. See you in the next video.